Welcome back, everybody. Last time, we thought about adding up information over surfaces. All right, the setup here was that we had some two-dimensional surface, and we have some information, some function values at each and every point. And at each point, we could take a stick of our function information's height, stand it up, and if we do that at each point on our surface, right, we get this kind of mohawk going on for our surface, right? If any of these function values were negative, those sticks would be pointing out the opposite direction. And we want to get our hands on the net volume of this kind of head of hair that our surface has now through our function information, right? And so what's going to do that is our surface integral. And in order to compute this, right, first step, we have our 1-2-step process, very similar to our line integrals, right? We need to parameterize our surface with our vector function, handing us the x, y, z coordinates of our points on our surface, right? And we have some parameterization domain for whatever parameters u and v we're using. We'll have two of them since we have a surface, right? And once we have that parameterization, we can use our translation formula that tells us how to compute this surface integral, right? The idea here is the size of the cross product bit. That's giving us the area of a little chunk of our surface. And then we're scaling that by our function value to get a little chunk of volume. And then the double integral goes through the whole surface and adds these up to give us our full net volume. What we're going to be looking at today is the situation where we have a vector field going on in 3 space. And let's think about what we'll want to add up in that situation. Well, here, if we have a vector field in 3 space, let's think of these vectors, these green F vectors, as showing us how a fluid is moving around. And so we can imagine ourselves, we've submerged ourselves, we've kind of scuba dived, and now we're inside the ocean, and there's some current going on, our water is moving this way and that. And right, we have some kind of magical surface that we are magically suspending in 3 space, just kind of keeping it steady. Well, a natural physical question to ask is, well, how is our water moving across our surface? Right, kind of which way in general is it wanting to move? Is it wanting to move, in this case, more towards the top, or is it wanting to move down towards the bottom? Which way primarily is our water flowing through our surface? Well, to get our hands on that, unlike with line integrals for vector fields where we did tangential components, now to understand kind of what portion of this F vector here is moving across our surface, we want to look at the normal component. So here we'll actually, on this point here, we'll stand up a unit normal vector. And what we want to do is look at the normal component of our green F vector here. So right here, this signed length, this is our information that we want to grab at each and every point on our surface. So over here at this green point, we'll have another normal vector that we can stand up, and we can look at the normal component of our green F vector there. So here it'll be a little bit less than over here, that our first one. but still be positive since it's in n's direction. Over here, right, we have this green vector. It's kind of pointing down though. So over here, when we stand up our normal vector, unit normal vector n there, and grab the normal component, we're actually going to be getting this little box that's behind our unit normal vector. And so this one will be counted negatively as we go through and add all these up. And so this is the information that we're looking to get our hands on, the normal components of our f vectors. And what turns out to be true is that we have a nice computational formula for getting our hands on this. You may recall when we very first introduced line integrals for vector fields, the tangential components we got by taking f dot t. Well, here it works out very similarly. Normal components we can get with f dot product our n vector. And so that's the information at each and every point that we're interested in adding up, and we use that to make a definition. So we say that the surface integral of a vector field over a particular surface is the surface integral where we go through and add up at each point the normal component information f dot n. And the idea here is that if at the end of the day the value we get from this integral is, say, positive, well, that would mean that we would have integrals primarily that look like this, right, where we have these positive components where we're going the same direction as n, and we don't have as many negative components. And so physically that would be telling us that our water is mostly wanting to move in this direction of our normal vectors. And similarly, if it's negative, it'll be telling us it's primarily moving the opposite direction. One of the interesting aspects of surface integrals for vector fields is it involves a choice. At the point that we started with here on the surface, to draw a normal vector, I drew this vector pointing up, but maybe you're a contrarian and you said, I don't like that normal vector. I want the vector that's pointing kind of straight down, underneath the surface. And that would actually be a perfectly legitimate normal vector. And so it's perfectly fine to choose that vector. However, once we choose the direction for one normal vector, all the others are chosen. We always are going to choose our normal vectors in a consistent way so that they're always on the same side. So if you made the same choice as I did, this pink normal vector at the top, then you can imagine sliding that point around, then that shows us our normal vectors at each and every point. On the other hand, if you like this blue normal vector, if that's the normal vector for you, then you can imagine sliding that normal vector around, and so all your other normal vectors would also be pointing down. And so an interesting thing about this, the fact that we always need our normal vectors to be, on one side or the other, is that we're actually assuming that our surface has well-defined sides. And this is usually true, and we're not going to have to worry about this very much, but I want to talk about it because it's cool. So if we imagine like a plane or something like this, well, if we stand a normal vector, say up in this top direction here, and no matter where we slide that normal vector around on our surface here, we're going to be pointing that same direction, right? The plane has two sides. Or similarly, if we do a little wrapping and wrap this plane up into a cylinder, well, if we imagine, at the top point here, standing up a normal vector, pointing out, well, we could take that and slide it around our cylinder. We'll be pointing the same direction. We could wrap it around to these sides, be pointing on the outward direction. We're always going to be pointing that consistent outward direction. And so our cylinder has well-defined sides. A sphere also has well-defined sides. If you stand up a normal vector in the outward direction, spin that any which way, it's still going to be pointing outward, and vice versa, right? If you initially choose your normal vector to be pointing inward, slide that around your sphere, it's always going to be pointing inward. So our sphere has well-defined sides. An interesting thing is that not all surfaces do. For example, actually this one does. I forgot about this one. We could poke holes in our sphere and make some kind of crazy donuts. This kind of a two-hole torus is, we say, orientable. It has well-defined sides. You can take a normal vector and move that point anywhere you like. We're still going to be getting a consistent direction. All right. But not all surfaces have this property. For example, the Mobius strip does not have well-defined sides. So this is not a surface that we can actually do a surface integral on. We say that this surface is not orientable. And so the Mobius strip is where you take this kind of a strip of paper in this case, and instead of kind of just wrapping it back on itself and forming a cylinder, you give it a little half twist before you connect it back up. And so there's a nice little animation here based on a painting by Escher that shows that we don't have this well-defined sides. And so here we've got these ants kind of crawling around this Mobius strip. And you can imagine here in front of us we have this ant, and so it's defining a normal direction. You can imagine, like, you ever seen those documentaries where like the fungus like sprouts out of the ant's head? Well, we can imagine that happening, right? And it gives us a normal direction. And so let's watch what happens as this ant kind of takes a walk around the Mobius strip. All right, so he's still moving around. We can imagine the normal vector poking out from his head. All right, so now it's kind of pointing, directly into the computer screen here. Now it's kind of pointing down, and notice he's gotten back to the same point on the Mobius strip, but now he's facing the opposite direction. And so this is exactly why we can't have a consistent choice of normal vectors on a Mobius strip, and so it wouldn't make sense to talk about a surface integral there. So that's just a little fun note. Things are good on surfaces like a torus, on spheres, on cylinders, on planes. These more perhaps familiar feeling types of surfaces. Things are all good. Another note is what happens if we choose a different direction. Well, things are just going to change in sign. So for example, here, if you chose this blue normal vector as your favorite normal direction for the surface, well then this green vector, showing our fluid motion, is still the same, right? The water is moving however it's moving, but now the normal component that we'd see is the same red box, but now it would be facing behind the blue normal vector. So the same red box would be counted negatively if we chose the opposite normal direction. And that would be true at each and every point. Everything just flips, and because of that, if you choose the opposite normal direction, you get what you would have gotten, but negated. All right, so that's kind of getting a feel for geometrically, intuitively, what these things are, what these surface integrals are computing in the presence of a vector field. But how do we actually algebraically compute these? Well, they're surface integrals, right? Right? And so we compute them just like we would any other surface integral. Right? We have our two-step process for success. And what's cool is that similar to our line integrals for vector fields, our surface integral for vector fields have a nice simplification that happens as well. All right, so step one, we need to parameterize our surface S with some vector function on some region D, telling us what U's and V's we're using. Second, we need to translate our integral. Right, in our translation formula, this is just straight taken from the top of these notes here. Right, and we have our handy mnemonic, multiply by the size of the cross product of the two partial derivatives of our parameterization. And this is what our surface integral becomes, what it translates to in terms of our parameterization. But what's really cool is that there's actually a nice way that we can write our cross product RU cross RV. And so we can see that in this picture here. We saw last time when we were talking about where this size of the cross product comes from, if we're on a point on our surface, our two partial derivative vectors, RU and RV, give us tangent vectors to our surface. Well, if we have two tangent vectors to our surface, then we have a clean way, I claim, of finding an orthogonal vector to our surface at this point. And let me back up just a sec because I misspoke. RU cross V is not what we are trying to describe here. Erase that from your memory. What I claim is that's this unit normal vector. I claim that we have a nice way to describe in terms of our parameterization. Okay, so back to our picture. Our partial derivative vectors give us two tangent vectors. Well, once we have two tangent vectors to a surface, if we want something orthogonal to that, well, let's take the cross product, right? If we take, I guess in this case, if I want it to be pointing straight up, then that's going to be, in this case, think about the right-hand rule, this would need to be RV cross RU. And this orthogonal vector to our surface, right, it's probably not going to be unit length. And so in order to fix that, well, we just need to scale this thing, right? Scale it by its size so that we end up with a normal vector. So our n is, with our picture here, or maybe I'll annotate it right here. So this is length 1, RV cross RU scaled by the size of RV cross RU. That would be, this picture with giving us our normal vector that's pointing up. Maybe our normal vectors were pointing downward. Well, if that was the case, then our normal vector formula would just be the opposite direction, right? Or it'd be RU cross RV divided by the size of RU cross RV. But what I claim is that these two sizes of the cross products, these are the same. Just because if you take two vectors and you cross product them and flip them, it's the same length, just pointing a different direction. So whether it's this light blue formula or this dark blue formula, what's going to happen is that the size of the cross product cancels out, either in that situation or this one. And what we're left with is just what's up top. RU cross RV, or RV cross RU, right, depending on what direction we want our normal vector to point. So this is our nice translation formula for surface integrals of vector fields. We end up not having to worry about the size of the cross product, we just need the cross product. Whatever that is in the correct order, we'll take the dot product with our vector field. Right? And as per usual, we'll make the substitutions from our parameterization, telling us what x, y, and z are. Because we have this nice simplification that happens, we do have a little bit of notation that's introduced to describe the surface integral for a vector field. And again, this is kind of analogous to our notation that we had for line integrals of vector field, right? We had this kind of funny notation, f dot dr. Here, we use the surface integral of f dot ds hat. That's the notation that we use for the surface integral over a vector field. And the language that's used is flux. We say that this is computing the flux of our vector field across our surface. All right, so now that we are ready to go with our translation formula, let's put it to work with an example. So here we have a surface hanging out in 3 space, and we have some vector field, right? And so we can't see what this looks like, but right, this vector field is doing something. It's has arrows attached to each and every point in 3 space on and off our surface. Right, those are incredibly accurate sketches of the F vectors. Let's use our formula from above and find the flux of our vector field across this surface in the normal direction shown here, pointing towards the YZ plane. And again, this language of flux, all this is telling us to do is to compute our surface integral, right? I guess, in whichever way you want to write it. So pause the video and see if you can follow our 2-step process, parameterize our surface, and then translate our flux integral, and see how far you can get in working through. All right, well, let's talk about this one here. So here, our surface is a nice clean graph of a function. Y is a function of x and z, and so we can take that formula and just plop it in where we see y in our parameterization. And so we get x squared is z, and we just want to know, well, what x's and z's do we do this for? And so looking up here, our shadow is actually in our picture, just x's from 0 to 1, and z's from 0 to 4 gives us this rectangular shadow of our surface here in the xz plane. All right, so here, this rectangular region, that's kind of our our d in the language of our notation up above. All right, so once we have our parameterization, we can now go ahead and translate our integral. And so we have our translation formula from above for our surface integral. And so we know that we're either going to get, for us, Rx cross Rz or Rz cross Rx. And the question is, which order do we want? And the way that we can find that out is actually geometrically, just by drawing Rx and Rz, those partial derivative vectors on our surface, and then using the right-hand rule to see which direction we're going to be pointing. And so the idea here, for example, with drawing Rx, the question we ask ourselves is, okay, well, if I moved along my surface just by increasing my x parameter, which direction would I be moving? And then draw an arrow to show that direction of movement. So for example, up here on our surface, if we imagine ourselves at this point here, that's corresponding to maybe this point here in our domain for our parameterization. Well, if we stayed on our surface while increasing the x parameter, where is that going to move us? Well, that's actually going to be pushing us, further out. It's going to be pointing us this way as we kind of want to move up along our curved surface here. And so that's actually the picture of Rx that we would get at this point. Maybe another, if you don't like that point, thinking about it there, we can imagine starting at the origin. Well, where are we moving? If we moved x, we'd be moving, this direction. That's another picture of Rx. Similarly, well, what if we're at this point, but we now crank up our z parameter? Well, that's going to move us just up along our surface. And it's important to remember that we are moving always along our surface, so that at this point we don't just magically shoot off our surface. We always kind of move along our surface for our partial derivative vectors. And similarly, at this point, we could imagine moving z, and that's going to move us vertically. So wherever feels most natural to get the picture, we can get it there. And then looking, I'll just kind of hone in on this picture. Well, which order is going to, through the right-hand rule, point us in the direction of n? Well, we'd have to start our fingers in the z direction and curl them to the x if we're going to have this work out. Let me see if I can get a little picture here. Right, so here's our three-fingered right hand, and our thumb is pointing up this direction. All right. And so it's going to have to be Rz cross Rx for us. Rz cross x points us in the direction of n. All right, so once we know that, then we have what we need, and we can just start computing and put pieces where they go and wrap it up. All right, so from our initial parameterization here, we can take our partial derivative vectors, our z, so we get 0, 0, 1, and partial derivatives with respect to x. And then we'll take those two vectors and take their cross product. just like we would any other two vectors. Right? We have our setup here, and we have our minus in the middle component. That always should be there. We go through and do our little minor determinants to come up with our components here. And here is the vector we end up with for our cross product. And so that will be what we plop in right here in our translation formula. Over on the left side of this formula, not move down that far, our vector field finally comes in. We actually haven't been really using that at all up to this point. We just literally replace f with what it equals. And once we've made these substitutions, we can take the dot product, right, as we would just any other two vectors, multiply their x components, right, and add up what we get when we multiply the y components and the z components. All right, so no more vectors going on, just get a scalar function at the end of the day. However, notice the two variables that our double integral wants to be in terms of are our parameters x and z, but we have a party crasher y over here, and so at this point this is where we want to sub in from our parameterization. Right, in our parameterization, scroll up just a sec, in our blue box here, telling us that x is x, y is x squared, and z is z. And so we'll make those substitutions here, swap out y with x squared, so then we get x times x squared, so x cubed. And this is what we end up with for the function that we are now just doing a standard double integral for. All right, and so here we've also included our limits of integration. Right, our region D is just a nice clean rectangle, so we can just pop those bounds up there. And at this point, we could just start antidifferentiating and evaluating, work through this. I'll leave the details for you to work out on your own. At the end of the day, we should get down to -2 for the value of our integral. And here, just looking at the sign of our result, that negative, thinking physically, this is telling us that our water from our green vector field is primarily moving in the direction opposite our chosen normal direction. So back up in the picture, these green vectors, what they actually look like if we had them sketched, would primarily be wanting to move this opposite direction, towards the xz plane, opposite this chosen normal direction that we had. So that would be how our water is actually wanting to move. All right, that's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.